Part 3. If you have made it this far, give yourself a gold star. Actually, go ahead and give yourself a star in any color you choose. All right, let's continue looking at light as a wave. Next topic is single slit diffraction, which doesn't really make sense on the surface. If you can kind of think like, oh yeah, light from two slits makes sense because light from one slit will interfere constructively or destructively with light from the other slit. But lo and behold, when you shine light or another wave through a single slit, if the slit is the right magnitude, similar to the wavelength, you still see an interference pattern, meaning you still see brights and darks. So how's that possible if there's only one slit for the light to interfere with? Well, without getting into too many of these specifics, the short version is if you imagine all the light going through that slit, it's as simple as light waves from one part are going to interfere with light from another part, depending on how the angles work out and some math that we're just going to kind of glide over, like sledding down a mountain on a fresh coat of snow. But due to some math and geometry things, depending on the angle here to the spot that we're looking at way off at the screen, they can add constructively or destructively. So similar to how we saw with two slits from the last set of notes, if we look at the light that is directly right ahead or the point in the center of the screen, all the light rays go straight to that point. They travel the same distance to get there. So therefore, they're in phase and you see a bright spot. When we see a dark spot, some of the rays are going to add up with other rays that are exactly half out of phase or out of phase by half a wavelength. So they cancel each other out. So the ones they've highlighted here for this dark spot, this ray travels an extra distance of 1/2 lambda compared to the one down here. This one travels an extra distance of 1 full wavelength lambda. So those two would cancel each other out. If you look at a bright spot, the rays will add constructively. So these two, the half lambda and the 3/2 lambda, would actually be in phase with each other, and they're going to add to give you a bright spot. And in other locations, they give you dark spots. We're not going to go into too many specifics about the geometry behind that. The textbook has a more thorough explanation. But if you can understand for a single slit how light from one part of the slit interferes with light from another part, the same rules apply. If they are a whole number multiple of lambda shifted off from each other, they'll add to give you constructive interference. If one of them is shifted off by half a wavelength compared to the other, they will give you destructive interference. We'll talk about how the equation works and what it means. But if you can understand that light from one part interferes with light from another part, you are good to go. Another important thing, when you look at that equation for a single slit, d sine theta equals m lambda, that's identical to the equation we used for a double slit in the last set of notes. So good news, it's the same equation. There's only one equation on the equation sheet for both single and double slit. But bad news is that it has a different meaning when we use it for a single versus a double slit. And we'll get to that in a second. So this is what a single slit pattern looks like. Here's a graph of it. Here's what it would look like here. So it's kind of similar to what we saw with the double slit, but the central bright spot is a whole lot wider. And another thing that's going to be different is when we use this equation, d sine theta equals m lambda, it now means kind of the opposite than we had before. So when we use this equation for double slit in the last set of notes, d sine theta equals m lambda told us where the bright spots were. Now, when we use the same equation for a single slit, it tells us where the dark spots are. So before, the whole number version times lambda gave us bright, but now it gives us dark. Another thing that's a little different for single slit is the maxima. The bright spots don't line up exactly between the minima. It's a little more complicated to calculate those, so I'm not going to make you do that. This equation does not do it. If you just put in the m plus a half, it doesn't give you exactly where those bright spots are, so that's a detail we don't have to worry about. And like I said, the biggest thing that makes this pattern different is the fact that this central spot is so much wider than the others. It's also brighter, a lot brighter than the others too. You can see that in the pattern here. So single versus double slit. Here is a single slit pattern. Here's a double slit pattern. And if you look closely at those, what you're seeing when you look at a double slit diffraction pattern is really this bright, dark, bright, dark, bright, dark, bright, dark. This is what we would expect from the double slit equation, but it's sort of overlaid on top of this wider pattern that we see from a single slit to give us the bright, dark, bright, dark, bright, dark, sort of within this bigger envelope that lines up with a single slit. And you can see back to this slide, the dotted line shows you what you would see with a single slit, and the individual bright darks show you what you'd expect from a double slit. The d sine theta equals m lambda for your bright spots. But what you're really seeing is the two of them combined. And it gets a little more complicated than that as you see more and more slits. You can definitely do more than two, but we'll sit on that for a second. Next slide, really important. This puts all of the stuff you need to know about the equations into one place. So here's the equation as written on the equation sheet. D sine theta equals m lambda. This is the only version that's given. So this second version, where you switch out the m for m plus a half, not given on the equation sheet. You just need to remember to make this yourself. Good news is it's not hard to make. But if you use the equation d sine theta equals m lambda as written, for a single slit, that tells you where the dark spots are. As written for a double slit, it tells you where the bright spots are. If you have a double slit and you're asked to find the darks, you need to know to switch out this m for m plus a half. And because single slit maxima don't occur exactly in the middle, you're not going to be asked where those appear. So all this information, you need to sort of remember and just memorize what they mean for the different ones. But recall that this is the only one that's given on the equation sheet. All right, last thing we got to touch on is diffraction gratings, which you saw when we did intro to optics lab stuff last week or a couple weeks ago, depending on when you're watching this. And a diffraction grating is similar, except it's not one slit, it's not two slits, it's a ton of slits together right next to each other. You can see this one here is labeled as 600 lines per millimeter, or the equivalent of 600 slits lined up next to each other for every millimeter of the diffraction grating that you're looking through, which is a lot. So how do these things work? You basically have tons and tons and tons of slits lined up next to each other. And there are a couple ways you can do that. The ones we saw were transmission gratings. So those were slits that blocked some of the light and let some of the light pass through. You can also have reflection gratings, which instead of a bunch of slits are kind of like a bunch of little mirrors lined up next to each other. That's actually kind of what's happening if you look at a CD or DVD or Blu-ray. You have tiny reflective lines of information really, really close together, which means you can get an interference pattern by shining a laser at a DVD. That's also why you can see the rainbow if you look at a DVD in white light. But what these do is they follow the same equation as a double slit. D sine theta equals m lambda, and they follow the same conventions for bright and dark that you'd expect for a double slit. So this equation as written gives you the brights. You can find the dark spots if you switch out m for m plus a half. But due to some math that we'll again skim over, you can read about it in the textbook if you like. The more slits you add just gives you thinner, more clear peaks from the more slits you add, you have the same ish number of bright spots, but they are more well defined and they're thinner. So this is comparing what you might expect from a double slit. When you have a diffraction grating, you can see that you still end up with the same number of major peaks, but they're clear, they're less washed out, and they appear more as single lines. Here's what happens when you shine two different wavelengths through the same diffraction grating here. You can see that d sine theta equals m lambda. Tells you that if you have a bigger wavelength, you have a bigger angle or bigger theta. So that's why for the first order fringe, red, which has a wavelength of 700 nanometers, is wider than blue. And same for the second. Red is wider than blue. If you shine white light through a diffraction grating, that's why you can see a rainbow. That's when we put on the chemistry paper fun glasses and looked at the lights. You can see rainbows spreading out because white light has all the visible colors, Roy G. Biv, from 400 to 700 nanometers. And based on the equation, d sine theta equals m lambda, you see a slightly different angle for each wavelength. So that's one of the ways that you can split the visible spectrum. This shows you the effect of a diffraction grating. So if you start with one slit and keep adding more slits, you can see that every time we add more slits, we have kind of the same number of bright spots or the same number of major peaks, but those spots get more and more well defined. If you go all the way to a diffraction grating, you get some really clear points when you shine it, laser through it. And we'll do a lab where we'll see that, where you'll get to experience that as well. So that is about it for double slit, single slit diffraction. The big thing from here on out is practice problems that we will get to next week.